Okay, we're going to solve the transient state of a series RC circuit. So first the circuit. Here it is with a single source of EMF, a single resistor, and a single capacitor all in series. By the way, if you can take a more complex circuit that contains multiples of these and reduce it to this, then it can also be solved with this. It's just now the capacitance might be a combination of other capacitors and the resistance might be a combination of other resistors. All right? Okay, the first step is to write the differential equation, and we'll use Kirchhoff's loop rule for that. We know that a single loop circuit, the change in voltage should be 0, so I'm going to go clockwise around here, and here's what we'll get. The EMF of the battery minus IR, which is the negative voltage produced by the resistor as the current flows through it, and then the capacitor charges in the opposite polarity as the battery. Positive collects on the top, negative on the bottom, so that's also negative. And the voltage on a capacitor is always the total charge on it at the time divided by C, and that equals 0. It's differential because that right there, I is dq dt. So this contains a function and its derivative. Q will change over time, I will change over time. So we get EMF minus dq dt times R minus Q over C equals 0. Now I'll do some algebraic manipulation to this in order to put it into an easily separable form. So once I do that, it's a couple of steps. I'll end up with dq divided by Q minus E over C, and then that'll all be equal to negative dt over RC. And again, it's just algebra that turns this into this, and we do that so that we don't have to U sub for the Q function. Now it's just in the form of a natural log is equal to dt over constant, all right? Okay, now we integrate both sides. So I'm going to integrate this side from 0 to Q, the specific charge at that time, and I'll integrate this side from 0 to T. Again, we're assuming there was 0 charge at the beginning, so this is at the time equals 0 stage where the switch is first closed, and of course time is 0 and it runs to T. Okay, the right side of this is easy. This just becomes negative T over RC. The left side, though, is a natural log, so it's going to be the ln of Q minus E over C, and then that'll be evaluated between 0 and Q. Let's just work on this left side for a little bit. We know it's equal to that. Okay, plugging in the top limit, that's going to be the ln of Q minus E over C, and then plugging in the bottom limit minus the ln of negative E over C. And we know the rules for natural logs means that this is the log of the ratio of this to this. So the left side is also going to be ln of Q minus E over C divided by minus E over C. And of course that denominator applies to both numerators, so this is going to be the ln of 1 minus QC over E. And that becomes the left side, so the full integral is right there. We can now write that ln of 1 minus QC over E is then equal to negative T over RC. Now it's time to exponentiate, so I take e to the x both sides. This side just becomes 1 minus QC over E, and then the right side becomes e to the negative T over RC. And I can do some more arranging. This moves over, this moves back, and then I can multiply by the reciprocal. So Q of T then, the charge as a function of time, is going to be equal to E over C, and then that's times the quantity 1 minus E to the negative T over RC. The final two steps are just window dressing. E over C looks familiar when basically the capacitor is fully charged. It will have its final charge on it, sort of Q max, whatever it's going to charge with in the steady state when equilibrium is reached. And that's actually going to be when the charge on the capacitor is E. And so the Q at that time is going to be equal to the total charge at that time, which will be equal to the battery voltage over the capacitance. So E over C is this Q max. So I can go ahead and change that. So this becomes Q max. And then the other change I can make is that we generally call the denominator of any exponential function, we call that tau, and tau is equal to RC. So the final form then of Q is going to be Q of t equals Q max times 1 minus e to the negative t over tau. And this is the transient equation. We can use that to make predictions on what the charge on the capacitor is as a function of time. In addition, I can take its first derivative, d dt, and that will be equal to Q. So dq dt, and that'll be equal to I. So I'll have I of t. I can then use I to describe the voltage across the resistor as a function of time. Because Q is also part of the voltage across the capacitor, I can say VC is going to be equal to this function Q over C, and that'll give me the voltage as a function of time. So as a result of that, I can find the voltage across the capacitor, the voltage across the resistor, the current, and the charge on the capacitor, all as a function of time, just as a result of that one differential equation. Okay, in class, we'll work this out for the other case, which is when it's discharging.